Hello guys, welcome back to my channel Gamma Die Gamma. Many apologies for the delay, but there was just too much noise in my dorm. Like people they procrastinate, they work in groups in the lounge, so I can't record there. And then I have a roommate, and my neighbors they're noisy, so I can't record in the rooms. But now I'm finally I took the time to actually record one video, and this is special because after a long time this is a physics problem. So let's get started without any further delays. Okay, so the physical system that we have to describe is a two block spring system. This block has a mass m, this block has a mass m. I don't know, call this block 1, call this block 2. We have to write equations of motion for both of the blocks. So let's go classical mechanics. Let's go all Newton's laws of motion on this guy. So assume that this is like the starting point. If this is like 0, and just to initiate motion, we displace the first mass by an amount x naught. Okay, these are the initial conditions at time 0 just for this mass. At time 0, this mass is at a distance of call this d. So this guy is at distance d, the mass 2 at time 0 initially. So I mean, we know that they're going to execute a simple harmonic motion, but to initiate that we need to displace the first mass by a bit x naught. Okay, now let's get more general. Now, because now we have to find equations of motion. So assuming that the displacement of mass 1 from this reference point 0 is an arbitrary distance, say x1, and at the same time the displacement of mass 2 is x2. Okay, we can use Hooke's law, saying the restoring force is equal to negative k times the displacement from the equilibrium point, and we want to set that equal to ma. I'm writing a, acceleration, as the second derivative of the displacement. That's why the two dots, the second derivative with respect to time. Okay, so for block 1, what we are going to do is we have the mass of block 1 times whatever displacement displacement it is covered, and the second derivative of that, which will basically give the acceleration at that point, at that displacement x1, or more precisely at that time, is equal to the effective spring constant, because now there are two springs. If the spring constant of this first spring is k and even this bottom spring is k, we'll have to do something about them if we want to consider them as one spring. So I'm writing k effective. We'll do calculations later. Negative, because the restoring force is always opposes the direction of displacement. And now what displacement do I take? x1. Well, it might seem tempting, but not quite, because we want the effective displacement, the effective change in length of this spring. I mean, think about it this way: if x1 and x2 are same, then there will be no effective stretching or compression of the spring, so there should be no restoring force. That's why we want the difference in their displacements x1 minus x2. And this makes sense because if x1 is greater than x2, I mean if this is closer at a given time, then this is trying to take the spring away. The spring will get compressed in this direction, and therefore it will basically have a restoring force this way for block 1. And that we see that because acceleration of block 1 is this way and then restoring force is this way, and we have a negative for that. And similarly, if x2 is greater than x1, the spring will get stretched this way, and well, the block 1 will get pulled, not pushed by the restoring force. Okay, and we can do this for block number 2 as well. So m times x2 double dot, this Newton's second law basically for block 2 is equal to negative, again same effective spring constant, but this time x2 minus x1, because now the direction is changed, because if x2 is greater than x1, there will be a stretching in the spring in this way, and then the block the restoring force will try to basically oppose this stretching in this way, and then since if the acceleration is in this direction, the positive direction, the restoring force is opposing this forward acceleration. That's why we have a negative. And if you don't want to look at this this change in order as the direction of the restoring forces, it's fine, because what you can do is you can draw, say, the free body diagram of this spring, these two springs rather, and then say, well, if if we tested the first equation, so if there is a restoring force this way, which is k effective times x1 minus x2, then since there is no, well, the reaction force on the spring will be this way. If the mass is going that way, the reaction force, the same magnitude reaction force, will be going this way. And then similarly, the reaction pair is this way. And so these guys, they have to be equal and opposite, because there is no net force acting on the spring. That's why you can see like the signs are like inverted in both of them. It's because of this action reaction pair on the combination of springs. Now, just to find the value of k effective, think about it this way. We have two springs. Just for this case, assuming we have like one mass, m dash, if the mass displaces by some amount, delta x, both these springs have to displace by the same amount. Because if one displaces less than the other, the mass will basically have to, be tilted on this table, and we won't allow that according to our physical systems. So, the delta x in both the springs has to be same, and assuming they have like different spring constants, so k1 and k2 for example. If we want to replace both of these springs by one common spring acting on m dash, we would have to basically write an expression for the force. So the net force or the effective force due to the spring is the force due to this first spring plus force due to the second spring. Well, by Hooke's law, this is negative k effective times delta x is equal to negative k1 delta x negative k2 delta x. And as I said, delta x for the effective spring for each of them individually are same, so we can cancel this out, cancel the negative out also. So K effective is K1 plus K2, and this holds true when springs are in parallel like this, and that's exactly our case. So K effective is just sum of the individual spring constants. So K plus K, K effective is K plus K, giving us 2K instead of K effective. So our equations are now as follows: mx1 double dash is equal to negative 2K x1 minus x2, mx2 double dash is equal to negative 2K x2 minus x1. Okay, now how do we solve this differential equation? Well, since both masses are the same, we have a great advantage here. We can add both of them. When we do that, we have m times x1 double dot plus x2 double dot is equal to, since these displacements are like negatives of each other, they can cancel out to 0. Mass will never be negative in any system that we consider to study, which means x1 double dot plus x2 double dot will have to be 0. Now if these variables are sort of intimidating, let's change the name of these guys. So x1 plus x2, call that y. If we differentiate both sides twice with respect to time, x1 double dot plus x2 double dot is indeed equal to y double dot, because the derivative is distributive over addition, which means we have y double dot is equal to 0. And this differential equation is pretty easy, because think about it this way: what function differentiated twice, what function of time differentiated twice will become 0? If you have a good command on derivatives, you might know that y will have to be a linear function like a plus bt, for example, but y was x1 plus x2. Now we want to find a and b, so we need to look at the initial conditions. So if we plug in t equals 0, this b term goes away, so we have x1 at 0 plus x2 at 0 is equal to just a. Well, x1 at 0, as I said, was x naught. x2 at 0 is at a relative distance d from, if we consider this as to be the reference starting point, like this entire distance is d. I can call that to be a. And for b, we'll need to differentiate this equation with respect to time. So we have x1 single dot plus x2 single dot is equal to just a. But now another initial condition that is probably evident, or I should have said, is both of these masses are at rest at time equals 0, which means these are velocities, right? Displacement differentiated with respect to time once is velocity, and both of these guys are 0 because both blocks start from rest. So a is 0. Oh, I'm sorry. When we differentiate, we get a b. I'm so sorry. Yeah, and b is 0. Okay, so by this we know that x1 plus x2, we can substitute back into this equation, is x naught plus d. Fine, good information. Yeah, good information. Good to know. Now what do we do? Well, we added the equations. Let's subtract them. When we subtract them, we basically have m x1 double dot minus x2 double dot is equal to negative 2k x1 plus 2k x2 plus 2k x2 minus 2k x1, which just turns out to be negative 4k x1 minus x2, and we have m times x1 double dot minus x2 double dot. Now notice this, we can do a slight variable change here. Let capital X equal x1 minus x2. So x2 double dot is x1 double dot minus x2 double dot, similar to the y case. So we have m times x2 double dot is equal to negative 4k capital X. So capital X double dot is negative 4k over m times x. Now this is one of the classic differential equations, and you think about it this way: what function when differentiated twice with respect to time, gives the negative of itself. And this is a really popular differential equation. I'll probably make a video on this because I can't explain that in detail. The solutions for this differential equation are some cosine, so call that a times cosine of this quantity, but square root 4k over m times t, because it's a function of time, and also a sine, because see, we could write in cosine individually or a sine individually, but since this is a linear differential equation, we prefer to have the general solution written as a linear combination of individual solutions. And then we can impose the initial conditions like we always do. So take t equals 0, sine will just vanish, x, which is basically x1 minus x2, is equal to a, and cosine of 0 is 1, so it's just a. X1 at time 0 is x0, and x2 is d. So a is just the difference of these guys. Now for b, let's differentiate capital X with respect to time. So we have x1 dot minus x2 dot is equal to negative a times square root 4k over m sine of square root 4k over m times t, plus b times square root of 4k over m cosine of square root 4k over m times t. And again plug in t equals 0. The sine term will go, so we'll just have b times square root 4k over m. Again, now x1 dot and x2 dot at time 0 are 0 because blocks start from rest. So this entire b term will go to 0, which means in our original solution there is no sine component because the b is 0, which means our general solution x, which is x1 minus x2, can be expressed as just a, which is x0 minus d times cosine of square root 4k over m times t. We have an expression for x1 plus x2. We calculated that above. Let's see where that is. Yeah, x0 plus d. And we have an expression for x1 minus x2. These are like classic linear equations. We can solve them simultaneously to get x1 is just x0 over 2 times 1 plus cosine of square root 4k over m times t, and then there's the other d over 2, 1 minus cosine of 4k over m times t. That's x1. Now x2, if we just plug in x1 in any one of these equations, we will get x0 over 2, 1 minus cosine of square root 4k over m times t, plus d over 2, 1 plus cosine of square root 4k over m times t. Now one interesting thing is, if we want to use some trigonometric identities, we can make a simplification of this guy. So x0 over 2 and 1 plus cosine is 2 times cosine squared of half the angle. So that 2 and this 2 will go. So x0 times cosine squared of half of this will just be square root k over m times t, because square root 4 was 2, plus d, and then 1 minus cosine of some angle is 2 times sine squared of half the angle, so that 2 cancels off. Sine squared of square root k over m times t. And then similarly for x2 we can have a similar approach. Sine squared of square root k over m times t plus d times cosine squared of square root k over m times d. Again, equations of motion for x1 and x2 which are functions of time themselves, otherwise none of this would make sense. This is a system that evolves in time given some initial conditions like x0 and d and being at rest initially. So yeah, I hope you enjoyed this video, guys. This was like a physics attempt after many months, maybe a year, who knows. Anyways, so that's it. So please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math, and stay tuned for more content. Thank you very much.